Hey everyone, hope you're having a great Monday. Going to talk to you today about quadratics, quadratic equations, um, some stuff that you may or may not remember, and some stuff that will probably be new to you. Today we're going to talk specifically about vertex form, we'll talk about standard form, and we're going to talk about factored form, which is one that you may not have graphed from before, but we've talked about factoring, and so it shouldn't be too tough. So this is really just a lot of stuff that we need to get out of the way before we get into some more complicated things and talk about rational expressions in Chapter 2. All right, let's see what's going on. So first of all, we have to discuss what the heck is a polynomial. So a polynomial function is one that looks like this, and the notation here gets a little weird, but we'll get some examples. It'll be easy. So a n x to the n plus a n minus 1 x to the n minus 1 plus all the way down to a2x squared plus a1x plus a sub 0. So all of these a's, all of these a sub somethings, these are numbers and we call them coefficients. Coefficients. There we go. So a coefficient is just something in front of an x term. So an, we call that the leading coefficient because it's the first one out in front, the leading coefficient. And that n that's hanging out up there, we call that the degree. It's the degree. And it's got to be greater than 0. Okay, because if you had a degree that was less than 0 or was 0, it would either be an uninteresting polynomial or it would not be a polynomial because it has to be positive ends here that are decreasing. So something that we could have for a polynomial, let's take a look at some examples. So like, for example, f of x equals 5x to the fourth minus 3x squared plus, I don't know, x minus 1, something like that. So notice we don't have an x cubed term, but you don't have to have that. You just have to have some of these things have a number. So 5x to the fourth, that 5 would be our leading coefficient. And in this case, our degree would be 4. Okay. Those look some things that might or might not be polynomials here. So this first one, we have 4x cubed minus 5x minus 1/2. This one's okay. We've got a degree of 3. We have 3 terms here. We have a constant term over here, this 1/2. We've got a 4x cubed. Our 4 is our leading term, our leading coefficient. Leading coefficient. And we have these 3 terms here. And every one of them's got a positive exponent, so we definitely have a polynomial there. I kind of gave it away, but this one is not a polynomial because we have a degree here, or an exponent that is less than 0. So if we were to write this out, it would actually be 6 over x to the fourth, because negative exponents flip things to the bottom, minus 7. So this is actually an inverse relationship of some sort. It's not actually a polynomial. So in this case, we have one that's not a polynomial. Now the next one, this also we have an issue with. We have a square root going on. And nothing that we talked about had a square root. All of those ends, all those degrees had to be integers. This is no good. Now one thing we've been focusing a lot on is this is not equal to 3x squared plus 4x. Now if you didn't even see that, then great. Yeah, this is not the same thing because you can't split this up into the square root of the first thing plus the square root of the second thing. Cannot do that. Don't do it. I'm going to scribble it out because I don't want you to do that. All right. So this is also not a polynomial. Okay. This last one, though, this is a polynomial. We've got a coefficient in front of an x to the first power, and we've got a coefficient in front of an x to the fourth power. So the degree here might be a little tricky. The degree is actually 4 because it's the highest value of n we have. If you were to write this in what we call standard form, it would be negative 2x to the fourth plus 15x. So our leading coefficient is also negative 2. Our leading coefficient is negative 2, not 15. Just because it's written first doesn't mean it's in front of the highest degree. Whatever's in front of the highest degree, that's going to be our leading coefficient. So there's a couple things to see what a polynomial is and isn't. So there's some specific polynomials that we should talk about. I don't know if I have them listed here or not. I do. The constant function is just f of x is equal to some constant a. So like f of x equals 2. Not very exciting functions. That's a horizontal line right at 2. Okay, not a very interesting function, but it has a name, it's a constant function because it doesn't change. That's why it's called constant, because it's, well, constant. Now, the book does make a beef about the a being 0. If you have f of x equals 0, they actually call that the 0 function. So that's right at the x-axis here. They say that it's like a special case of a constant function, so just worth noting. A linear function, f of x equals ax plus b. Now you're all going to say out there, you're going to say, oh, Mr. Fransky, we always use m. That's okay. It's just a letter. It's a variable. You can use either one you want. So mx plus b is going to be a line. It's a linear function. Could look like that. Maybe has a negative slope, something like that. The one we're going to focus on today is the quadratic. So that's f of x equals ax squared plus bx plus c. So you see we just kind of keep adding degrees on here. Quadratic function has a degree of 2, and it makes a parabola. So you might have a parabola looks like this, might have a parabola looks like this. Okay. So depending on where it is on the graph, these a, b, and c are going to determine what our parabola looks like, and that's what we're going to focus on today. So we're going to start by talking about some transformed quadratics, which we've seen before. We saw these back in section 1.6, so it was about 2 tests ago now. We're doing the RST, the reflection, the stretch, the shrink, and the translation. So this first one, let's take a look at and write out our RST. So our reflection here, we have a negative out front, so that's over the the x-axis. It's going to change all of our y values, so that's a reflection over the x-axis. Our scale change, we have that 1/2 out front. That's going to be a vertical shrink. And then our translation, we don't have anything with the x like we do down here, but we are moved up 3 by that plus 3 at the end. So if we start with a parent function that looks like this is x squared. We've flipped over the x-axis, so this guy's going to come down to the bottom. Then we've shrunk it in half, so instead of being like this, it's going to look wider. It's going to be shrunk down. And then we have that plus 3, which will move it up 3. So move it up 1, 2, 3. We're going downwards, and we're wider. So it looks something like that. Okay. Now this next one's even a little easier because we have whole numbers dealing with. So let's do our RST again. No reflection this time. There's no negative in front of the x, no negative in front of the 3 there. Our scale change looks like we have a vertical stretch. Vertical stretch by a factor of 3 right here. And then our translation looks like we're moved to the left 2 because the x does the opposite thing we want it to. So left 2, and it looks like we're moved down 1 because the y does what we expect it to do. So if we were to graph this, shift to the left 2 and down 1 right there. There's our new origin. And it looks like we're going to be stretched by a factor of 3, so it's going to look skinny because it's been vertically stretched. So something like that. This form is a special form that we're going to talk about in a second here. It's called vertex form. So it's vertex form because we know exactly where the vertex went by just looking at that number and that number, because that's how much it slid left or right. Second one is how much it slid up or down, and that ends up giving us our entire vertex wherever it belongs. Cool. So let's talk more about that. Vertex form, that last function we had, 3 times quantity x plus 2 squared minus 1, is an exact, perfect example of vertex form. So what vertex form looks like, I'm going to use f here. F of x equals a times x minus h quantity squared plus k. Now if you think about this, about how this thing has been translated, that x, remember, it always does the opposite of what you want it to do. So if it was like x minus 5, I move it to the right 5. If it was x plus 6, I move it to the left 6. So that h is actually how much we're shifted left or right. So if we start with a parabola at 0, 0, wherever it goes left or right, that's where our vertex is going to go. That plus k at the end is also where it's going to go vertically. It came from the other side, but now we've got it over here, so it's plus. It's going to do what you think it's going to do. So the vertex of this guy, the vertex is going to be at h comma k. That's where it's going to be. So the vertex of this thing should be at -2, -1. Let's go back and take a look and see if that's rendered up. -2, -1. There's our vertex. Looks like it worked out pretty well. So, oh, one more. There we go. So we have our vertex here. We can see it very easily from what's going on because it tells us exactly what the translation is. And then that 3 out there, not a coincidence that we used an a there. This vertex form actually has the same leading coefficient as the final answer will. And that makes sense, because if you multiply this out and then you distribute the 3 is going to be in front of the x squared. So the first term of this thing is going to be 3x squared. There's going to be a whole lot of stuff after it. But we see our leading coefficient, and it's nice because it tells us exactly where the vertex is. So this vertex form is a really nice way to be able to see what's going on with a parabola. Another thing they mention here is what's called the axis of symmetry. The axis of symmetry for a parabola goes right through its vertex. So in this case, if we think about our parabola, we shift it left 2 and down 1. Our vertex now lies on that vertical line, x equals -2. And that's our new line of symmetry, or it's called our axis. Axis of symmetry. I have some questions today in your homework that ask about the axis of symmetry of a parabola. And it's just whatever the x-coordinate is of the vertex. It's the x-coordinate of the vertex. Okay? Because you're your axis of symmetry. All right, let's move on and see if we can figure out what standard form is. So standard form, we kind of gave away at the beginning. It's the ax squared plus bx plus c. But there's some interesting properties about the standard form that we want to look at. So I'm going to start by taking a general form of the vertex form, and I'm actually going to expand this to get the standard form. So we'll have a multiplied here by, if you have x minus h squared, that's x minus h times x minus h will FOIL. X times x is x squared. So I got a minus xh and minus another xh, that's minus 2xh. And then negative h times negative h is plus an h squared. And that's all plus k. So let's distribute that a. So we have ax squared minus 2axh plus h squared plus k. Now, what they want us to do here is try to figure out something in front of an x squared. Well, that's easy. So it's just ax squared. And then we pull this stuff out in front of the x. So we have negative 2ahx. And then plus, looks like we have an ah squared. I got the a in there, sorry. So we have plus ah squared plus k. So some interesting things that happen here. The constant term is ah squared plus k, but that's not too bad. The constant just kind of hangs out at the end. This negative 2ahx, we know that h is the x-coordinate of the vertex. So if we think about this, usually see this written as f of x equals ax squared plus bx plus c. And if we know that h is the coordinate of the vertex, we can solve this. So b is always going to be equal to negative 2ah, right? Because that's just what's in front of the x. So if we solve for h, we get h equals negative b over 2a. Now you may have seen this before. This is the x-coordinate of the vertex. So if we're written something in standard form, we're going to be able to find that by just looking at it. And then if you want the y-coordinate, some people say, well, you could take this ah squared plus k, but to get the y-coordinate, I would just plug it into the function. So the y-coordinate is going to be f of negative b over 2a. That's not so hard. So what I want to talk about now is we're going to take a look at some of the properties that we have for the vertex form, because, for the standard form, because these are some things that people have seen but may have forgotten. So we just showed that the vertex of this guy, the vertex is going to be at negative b over 2a, that's our x-coordinate, and then the y-coordinate, we just plug it in, f of negative b over 2a. Some other things that you may know are y-intercept is pretty easy to find here. And that's because the y-intercept happens somewhere on the y-axis. Every one of those points on the y-axis has the same x-coordinate, 0. So the y-intercept is just going to happen by plugging in 0 for x here. When we plug in 0 for x, that first term goes away. The second term goes away, so it's just y equals c. So that c value tells us what the y-intercept is, which is going to be very helpful for us. The x-intercepts are harder to get. The x-intercepts, you may remember this, are gotten by the quadratic formula. So there are two of them. X equals negative b plus or minus. That's where we get two of them. Square root of b squared minus 4ac all over 2a. So you remember my story. The negative boy couldn't decide whether or not he wanted to go to the radical party. Decided a b square, missed out on 4 awesome chicks, and it was all over at 2 a.m. And there it is. So some of the stuff that's good to remember, if you need to find the vertex, negative b over 2a, and then plug it into the function. Y-intercept, just y equals c, whatever's hanging on at the end there. And then the x-intercepts are given by quadratic formula. You could also use factoring or completing the square. But quadratic formula will work for you every time, and factoring is something that sometimes is not possible. Completing the square, I know, is our favorite thing for everybody. So just some of the things that we need to keep in mind when we're doing these problems. Let's take a look at an example of a standard form problem. So we're going to find the vertex, the x, and the y-intercepts of this equation, x squared minus 6x plus 8. So let's start with the vertex. We know the vertex, based on our formula, the x-coordinate is going to be negative b over 2a. So let's do that with this problem. So b is negative 6. So negative 6 over 2a, which is just 2 times 1. There's always a 1 out there in front if there's nothing there. And that gives us positive 6 over 2, which is 3. That's the x-coordinate of the vertex. So to find the y-coordinate, I have to plug it in. So let's do f of 3, which is 3 squared, that's 9, minus 6 times 3 is 18, and then plus 8. This gives us 9, let's see here, negative 9 plus 8, which is negative 1. So now we have our x-coordinate, which is 3, and we also have our y-coordinate, which is negative 1. So we have 3, negative 1 is our vertex. Let's do the next one that's easy. It's a y-intercept. So we just said the y-intercept is just c. Hey, that's 8. That's not so bad. So the y-intercept is just y equals 8. And now we can kind of start getting a decent picture of this. Our vertex is at 3, negative 1, right here. And our y-intercept's got to be up at 8. So we know it's going to be kind of a right-side-up parabola. We don't have are those x-intercepts. So let's see if we can figure those out and see if they go with my perfectly drawn graph over here. That's pretty pathetic. But let's give it a shot. So the x-intercepts, let's find them using the quadratic formula. So it's going to be x equals negative b, which is positive 6, plus or minus the square root. B squared is 36, minus 4ac. Well, a is 1 again. AC is 8, so it's going to be minus 32, all divided by 2a, which is just 2. Negative 6 plus or minus, see, this is the square root of 4. That's not so bad. All over 2. So that's going to be negative 6 plus or minus 2 over 2. Break it off. Negative 6 plus 2 is negative 4 over 2 is negative 2. And negative 6 minus 2, oh, brought in a negative. I'm trying to do what you guys do all the time. Mess up my negative signs. Let's see here. So we got positive 6 plus 2 is 8 over 2 is 4. 6 minus 2 is 4 over 2 is 2. So it looks like it goes through right at 4 and at 2, which isn't too bad for the graph I drew. So we found our x-intercepts, we found our y-intercept, and we found our vertex. And that's what we were asked to do. Cool. Now we're going to talk about how we go from standard to vertex form. And this problem right here is almost in standard form. I want to write it in decreasing order of the degree, though. So that's going to be negative 3x squared plus 6x minus 5. Now we have it in ax squared plus bx plus c. So for the vertex form, if you're just told to write something in vertex form, it's pretty easy. Because if we take a look, we see that the vertex form just has the same a value out in front. All we have to do is find the vertex, throw the a in the front, and we'll be done. So let's get back to here. So our vertex, remember again, that's going to be negative b over 2a for the x-coordinate. So negative b over 2a gives us a positive 3 over 2a, which is 6 times, oh, sorry, I'm doing the wrong problem here. Must be getting late. So here's our a, b, and our c. So our negative b is going to be a negative 6 over 2a, which is negative 6 again. So negative b over 2a gives us a positive 1. That's our x-coordinate. Plug that back in to get our y. So our y is going to be f of 1, which is negative 3 plus 6 minus 5. So this is a positive 3 minus 5 is negative 2. So our vertex is at 1, negative 2. Well, we know that that's going to be h and k, right? Because our vertex form is a times x minus h squared plus k. So our h is 1, our k is negative 2. We just plug it in. Our a value is our leading coefficient. Right there, it's a negative 3. So vertex form, f of x is negative 3, because that's our a, times x, we've got to subtract h, x minus 1 squared, and then plus k, which is going to be minus 2. And there is our equation for that parabola in vertex form. Not too bad. So now let's try going from standard to vertex form using completing the square. Completing the square. It does come back. So let's take a look here. We're trying once again to get this in the form a times x minus h quantity squared plus k. That's what we're trying to get. So we've got a plus k out here, so we probably just leave that alone. What we have to deal with is try to get this into a perfect square. So I'm going to pull that 3 out. We have 3 times x squared plus 4x. And I'm going to leave some space in here, because we're going to end up completing the square right there. And then we have that plus 11 out at the end. So to complete the square, if you remember, you look at this middle term, so you have to factor out the a, which we just did. Look at the middle term, divide it by 2, and square it. So it's always that middle term divided by 2 and squared. So I'm going to do 4 divided by 2, and I'm going to square it. That's 2 squared, which means I need a plus 4 here. Now, the reason I left so much room is because if I add 4, I better take it away too. Because I can't just add 4 to an expression. It's equal to something. So I can't just add a 4 willy-nilly and expect that it's going to be okay, because it would unbalance the equation. It would unbalance the equation. So now what I'm going to do is I'm going to link this negative 4 up with the 11. But in order to be able to do that, I have to distribute this 3 to it first. So that 3 times the negative 4, because I need the plus 4 to be able to complete the square here. So that's why I brought it in, because I need it to complete the square here. But I don't need this negative 4, so I'm going to put that out with the 11 to get the constant. So 3 times a negative 4 gives me a negative 12. So what I've got here is I have 3 times, I'm going to complete that square in a second, negative 4 times 3 gives me that negative 12, and plus 11. Now let's complete the square inside here. The whole point of adding that 4 was so I had a perfect square there I could factor. Looks like it's going to be an x plus 2 squared. Well, this is starting to look like what we're looking for. That's why we're using completing the square. So it looks like I have 3 times x plus 2 squared, and then negative 12 and 11 make a negative 1. And that's our function. So just writing it in a different form, in that vertex form using completing the square. And now we can talk about it. Our vertex is going to happen at negative 2, because it's the opposite of what we got there, and negative 1. That means that our axis of symmetry happens at x equals negative 2. That's kind of cool. That wasn't too hard to do. And that 3 out front there, that's going to give us that vertical stretch. So, once again, negative 2, negative 1. We've seen this before. There's our parabola, and it's going to be nice and skinny because it's got a stretch of 3. That's all there is to completing the square. Got a couple homework problems on that. Make sure that I wanted to give you one of the examples that looked like it. So let's talk about factored form. So we have another shot at this equation, this x squared minus 6x plus 8. This is the one that we dealt with before. We had to do the quadratic formula. And these roots seemed out to be really nice. So maybe there's a way to factor this equation. And when you factor, what happens is you get some more information. So let's try to factor this. You could do this with the x box. I'm actually going to do it with trial and error. So we're looking for factors here that multiply to 8 and add to negative 6. So my factors for 8 could be 1 and 8, or it could be 4 and 2. Well, 1 and 8 won't get me a 6. 4 and 2 look pretty good. I need a negative 6 and a positive 8, so both of those are going to be negative. We now have our factored form of this quadratic. So it's just, you have to factor it. That's all you have to do to get factored form. So this tells us really quickly what our x-intercepts are. Because the x-intercepts, they happen, so wherever the x-intercepts happen, that's going to happen when the y-coordinate is 0. So that means my f of x, or my y-coordinate, 0. So it's x minus 4 times x minus 2. Whenever you have factors lined up like this, they're all multiplied by each other. So the only way they're going to equal 0 is if one of them is 0. So either x minus 4 has to be 0, or x minus 2 has to be 0. So that means that either x is equal to 4 or x is equal to 2. So if we made a graph of this, 1, 2, 3, 4, right there, there's one of our roots, and there's 2. Those are going to be our 2 roots, which is what we found with the quadratic formula when we did it in standard form as well. But factoring, didn't have to do quadratic formula at all. It was really nice. So the other piece of information we can get from a factored form here, and we can see it in the standard form right above it, but that 8 is our y-intercept. Where did it come from? Well, take a look at this. It's negative 4 times negative 2. So we're going to focus a lot more on this tomorrow, this factored form. But all we have to do is look at negative 4 and negative 2. We say, well, our y-intercept is just negative 4 times negative 2, which is 8. So we just look at those two numbers there, and we're able to get that 8 value. So up here we go, 1, 2, 3, 4, 5, 6, 7, 8. It's going to be up here somewhere, and we can make our parabola because we know where the intercept is and we know where the x-intercepts are as well. Vertex is a little bit hard to get using factored form. You would have to expand it into standard form and then do negative b over 2a in order to find that vertex and the line of symmetry. Also though, I mean, it happens halfway in between the roots, so it's not that hard to find it by just taking the roots, adding them up, and dividing by 2 to find the average. That would work as well. But really what I'm concerned about is can you find the x-intercepts and the y-intercept when the equation is in factored form like that. So in general with factored form, that's where you're going to have something like f of x, so you have these factors. So it might be like x minus a times x minus b, something like that. Your x-intercepts are always going to be a and b, so it's just whatever you're subtracting there. Sometimes you might have an addition, so if you had like x plus 2 times x minus 1, something like that, our x-intercepts would be negative 2 and positive 1, because when you plug those in for x, that's what's going to give you 0. Sometimes you might see a problem like this as well, where the x and the number kind of switched back and forth there, but still, you're looking for 0 equals 3 minus x, or x plus 5. So this time, we set 3 minus x equals 0. 3 is still going to be your value there for x. What changes here a little bit is you have that negative, and when you have that negative in front of the x, that's going to change which way it opens. But we still have all the information we need right here. So x equals 3 is going to be one of our intercepts. X equals negative 5 from this guy over here is going to be our other intercept. So we have our x-intercepts at 1, 2, 3, and negative 1, 2, 3, 4, 5 right here. So we have our x-intercepts, pretty far apart. And then we can find our y-intercept as well by multiplying our two values here. Because when we FOIL this out, you could FOIL it all the way out if you wanted to, but what your constant term is going to end up being is 3 times 5, which is 15. So 15 is way up here somewhere. Let's say it's right there, though, just for our purposes here. And if 15 is up there, we have to intercept it up there, so it must come up like this and then come back down like that. So what the negative here does, flipping these, what it does, it makes it a frowny face parabola. It makes it go downwards. Because if we were to multiply this out, our a value would be a negative 1. In fact, let's just multiply this out. Looks like we would have 3x plus 15 minus x squared minus 5x. So altogether, that's negative x squared minus 2x plus 15. We see we have that negative out front there, and that's what signifies we have the frowny face parabola. Negative, sad face parabola. If it was positive, like we saw before, that's where we're going to have that right side up parabola. And that's how factored form works. We'll talk more about that tomorrow. So what's the whole point here? Well, there's this projectile motion problem that you see a lot in physics. You also see it in math quite a bit. And it's a quadratic, right? Because we have a squared value right there. That g, that's the acceleration due to gravity. It's 9.8 meters per second squared if you're dealing with meters, or 32 feet per second squared if you're dealing with feet and inches and that kind of stuff. That v sub 0, that's the initial velocity that something is thrown. I'm guessing you guys have seen this equation before. I know that they talk about it in advanced algebra. And that h naught is the initial height, or the starting height. So when you have all this information, you can actually create a quadratic that will be able to work for you. Let's try that with an example. So you launch your math book out of a catapult from the top of the school building, which is 36 feet high, at an upward velocity of 64 feet per second. And the question is, when does it reach its maximum height? What is that height, and when does it reach the ground? So we're going to use our equation. I'm going to steal it from over here. We got negative 1/2 gt squared plus v initial t plus h initial. And we're going to see if we can build an equation here. So they tell us things are in feet here. So we're probably going to be using that 32 feet per second squared. So we have negative 1/2 times 32 feet per second squared times t squared plus our initial velocity. Well, they tell us what that is. It's 64. So we have 64t plus our initial height. Well, it says the school building is 36 feet high, so it's 36. Negative 1/2 times 32 is negative 16t squared plus 64t plus 36. So here we have our equation for that math book being launched out of a catapult from the top of a building. And what we can do is we can use all of our fancy equations to be able to find this stuff out. So when does it reach its maximum height? Well, this parabola is going to look something like this. And when does that reach its maximum height? Well, it happens right here. What is that on the parabola? It's the vertex. So we just do negative b over 2a, which is negative 64, over 2a, which is negative 32. Gives us a time of 2 seconds. So that's where we're going to hit that maximum point. Now they actually ask what the height was, so we need h of 2. So that's going to be negative 16 times 2 squared plus 64 times t plus 36. And that gives us, let's see, 4 times negative 16, well, that's negative 64, plus 64 times, that should be a 2. That's my bad. So that's plus 128, so we had negative 64 plus 128 plus 36. So that gives us a positive 64 plus 36, which is 100. So it's going to top out there at 100 feet. It's a very high-flying math book. Then it asks us when it hits the ground. And when it hits the ground, well, that's going to happen right there. That looks a lot like an x-intercept, doesn't it? So if it's the x-intercept, we can use quadratic formula to find that. So that's going to be negative b plus or minus the square root of b squared minus 4ac. So that's going to be 4 times negative 16 times our c value, which is 36. All divided by 2a, which is going to be 2 times our a value, which is negative 16. Now, that's a pretty messy equation. I actually have this equation set up in Desmos, so we can actually just find that x-intercept by taking a look at it. So let's see if we can find it in our Desmos here. I'm going to keep our notation there. Let's go over to Desmos. I've got it graphed right here. So we have this negative 16x squared, and that's why it's down like a frown, because we have a negative value to start with. And that maximum should happen at 2, 100, which is exactly where it is. We found that by doing the equation with the vertex. And then over here's what we want. We want to know when it hits the ground. Looks like it hits the ground right at 4.5 seconds. We'll go back to our data here. So that must end up equaling 4.5 seconds. Looks like we changed to red for the very end. And that's all you have to be able to do. So, your homework tonight, what I'd like you to do is page 182, number 13, 16, 17, 34, 35, 37, and 61. It's also on the sideboard. It's also on Moodle. And what I'd also like you to do, it says in those two spots, it says you do some video problems as well. That's these, because there's really no good factoring problems in here. Tomorrow we're going to hit it a lot harder and do a worksheet. But what I'd like you to do is these book problems and also these factor problems. And for these, I'd like you to give you the x and y intercepts and sketch a graph. So remember, when you get the x and y intercepts, let's say it's like here and here, and then you have the y-intercept. You find that by multiplying the two numbers together. Be careful of negatives. You're going to be able to get a pretty good picture, if you can draw, unlike me. If you can draw a pretty good picture of that parabola, because it's got to go through all those points. And that's all you have to be able to do. So please email me if you have questions. If you want to see one of these homework problems done, or you want to see one of these maybe, just let me know, and I'll put it in the video for tomorrow. So I love you guys. That's why I'm here. I hope you have a great day. There was a riddle that I gave you on Friday after your test. I just wanted to give you another shot at it today if you didn't have a time to do it after the test on Friday. I will be giving the answer to this in tomorrow's video. So what's happening here is you have 1,000 pirates, and they're actually numbered 1 through 1,000. So if you're pirate number 1, you know you're pirate number 1. If you're pirate number 85, you know you're 85. If you're 762, you know you're 762. They have plenty of gold to split among everybody. Let's say like 1,000 factorial pieces of gold, so that you know that it could be split evenly among any number of pirates, 1 to 1,000. And obviously, if they kill some pirates first, then they'll be able to split the gold and have more for everybody that's still around. So what they're going to do is they're going to vote on whether or not they're going to kill pirate number 1,000. So they vote yes or no. Everybody votes. And if they decide to kill pirate 1,000, hey, that's great because they have fewer people, so they're going to be able to get more gold each person. So majority is going to rule, so you need at least half people to get to vote to kill the person. And if they do kill him, then they're going to vote on 999. They vote on 998, 997. They keep voting until they reach a spot where there's a deadlock and they cannot get a majority vote. So the question is, well, when are they going to stop voting? Like how many pirates will be killed and how many pirates will end up splitting the gold? So a good place to start here is to say, well, if they get all the way down to 1 pirate, he gets all the gold, right? If they get all the way down to 2 pirates, then pirate number 1 will vote to kill, pirate number 2 will vote to save, and they'll split it there. And to kind of keep going up from there and see if you start noticing a pattern. So think about it, and we'll take a look at the answer tomorrow. Love you guys. That's why I'm here. Have a great day.